Okay, so I have already discussed the OTA part as a concept, and as I also discussed the circuit. Today we shall start with some applications. These applications which few of them I will show you. As I said, there are many, but the major ones I will actually like to tell. And the first thing and foremost for which OTA is very popular is realization of active filters. What is the difference between active filter and a passive filter? That if you don't have any device, only RC or RLC circuit, we call it passive filter. Of course, please don't think that passive filters are bad or something. Passive filters are many times very good actually. But they have their own limitations many times because of the realization on silicon, and therefore it is better to go for active filters. We have already done in our second year active filters using op-amps, Salon key kind of blocks, which we say that we can always create using Chebyshev this or maximally flat filters, choosing the whatever you wish to have specs. You can have second order, third order, fourth order, nth order filter designs. More accuracy can be built, cutoff can be very sharp, can be slow, 3 dB down point can be shifted, all possibility exists. And if you are aware about the MATLABs, I think this is a very trivial job in the case of using MATLABs. So you do work in some case. The first attempt of any filter design should go on MATLAB so that you see the response and know what's going on. Okay. But we are interested more so in the realization of filters with using OTAs. And one of the problem with most of the filters requires higher frequency cutoffs, that is their bandwidths are required higher. And that means if you look at normal passive filter, it is time constant is 1 upon RC, frequencies are 1, omega is 1 upon RC. Either you reduce C, which at best you can create out of a MOS transistor with all parasitics there, everything there, that is not very small value as we think. Okay. So you can reduce R, but if you reduce R, silicon has a problem that it is limited on both sides. You cannot have very high resistance because the sheet resistance is not very high, so area it takes is very low. If you take a very low R, then the exactness of that R because of the variation in parameters like mobilities is very difficult to get 10 ohms, 1 ohms, it is very difficult. That means 1 ohm may become 2 ohms also. Okay. On chip there may be many which are varying drastically, it may be 50% variations. And therefore very low resistance or very high resistances are not greatly realizable on silicon. In circuit we can always say 1 ohm and fair enough, but when I do in silicon I find on 100 chips only 1 worked. Okay. So that's something which I am worried about. So active filters try to alleviate some of those problems, and therefore the OTA based filters have become very popular. Essentially what we are doing, we are replacing R by 1 upon GM, and we know GM can be because of feedback systems we can make much more accurate GM values compared to passive Rs, okay, and they are much more controllable by bias currents. So we can have a large value of variation on GMs for which, or even tunable, we can actually tune it back, okay, by feedbacks. So something which is great in the case of active filters we would like to see. Is that okay? Why OTAs are, and see GM is coming from an OTA. OTA output is essentially I out, therefore it is a transconductance amplifier. Let us start with the actual filters. Typical OTA as I shown here is it has a transconductance GM. And in the case of GM we saw in actual circuit which I showed you, if the K, the multiplying factor K is used 1, then small gm and capital GM are same, otherwise K times small gm is essentially the capital GM. And the way we said I out current is proportional to GM V plus minus V minus. So if we put V minus 0, obviously which we can do anytime, so this is I out is GM times Vn, and I out by Vn is therefore the transconductance. So all that we are now trying to see, can I use this block to create a GM circuit which then can be used to make GMC filters. Okay, so that's the basic idea behind all these choices. So let's see, is anyone anything, there is nothing much written, there is nothing great in figure. All that I am saying, I am trying to use I out to GVN. Is it okay? The kind of thing right now shown here is open loop. Okay, is right now open loop. Okay, but we like to use most of them in closed loop configurations. So let's say this is this I ground per se, and this is the OTA which you have started with. Okay, and then we always said I out is GM. Let's say right now GM is equal to GM 1 or whatever, if it is 1 you wish to put 1, okay, times Vn. Now if I say, if this is the system, I load it by a capacitor C, okay, is that okay? I can load this I out OTA, of course this are still grounded. Of course I may remove the ground soon, but right now I kept it. In real life what I am going to do is this. So now what will happen, the output voltage here is I out into j omega c. Sorry, I out upon j omega c, okay, impedance is 1 upon j omega c. So I now figure it out that I out has something to do with GM. There is some V in there sitting, so V out by V in has a function of GM by C kind of function. Is that correct? That's something I am seeing it here. So I said, okay, to control it better, of course I didn't show you, but you can always say this is my I bias which is controlling my GM, and now I do, this is my V out, I actually feed it back like this, and here I actually put the capacitance. This is loaded and with negative feedback. Okay. Why we normally don't do positive feedback? Because it will become unstable, because growth will start. Okay. So this is an interesting simple circuit. I can solve this now. I see something, few things, you just draw it. This is only step by step I am showing you. I could have directly written this and solved it, but I thought how do we realize this is how we started thinking. So my transfer function for this is V out by V in, and if I look now for any transfer function of a low pass filter, is it drawn, everyone? If you see a low pass filter, typically I am looking for, let's say, transfer function, what can be this, into omega. So I want ideally this kind of transfer function, sharp fall. But if I say that okay, it falls something like this, my cutoff is still the same, 3 dB point of a normal gain amplifier kind. Though whether you can tolerate this much is your requirement, you can decide how many 20 dB or 40 dB down you want. So additional poles may be required, additional some gains required, but otherwise a normal AS omega function or A j omega omega function, if it has a single dominant pole, it looks like a low pass filter. Okay, so that's the idea behind actually finding that V0 by Vn, if we find it as a function of omega and we get omega 0 as its known frequency, which is one of related to Gm and C, then I know what is the cutoff of this low pass filter. So if I use this last expression, you can see from here, this V out is connected to V minus, that is V out is V minus. So for this case, V out or rather V minus is V out. Okay. We also see one thing for this figure. What is V out essentially? I out essentially is GM times V plus minus V minus, or GM1 times V in minus V minus, which is V out. Is that okay? I just replace V minus by V out because that's the connection I did. Okay. Or if you look at this point and this point are same. So what is essentially V out, otherwise I can figure out? There is a I out current flowing in capacitor. So V out is I out into 1 upon j omega c. Is that okay? So if I write now this I out here, I get GM1 V in minus V out by j omega c is V out. Collect the term for V out, so I get V out 1 plus, okay, or rather if I would have done the other way, it doesn't matter, 1 plus GM1 by j omega c is equal to GM1 upon j omega c into Vn. If I find the transfer function, gain function, which is V out S, if these are all omega terms, j omega times V in, which is also a sinusoid, then it is equal to GM1 by j omega c divided by 1 plus GM1 upon j omega c. I divide numerator denominator by GM1 by omega c, so I get 1 upon 1 plus, please remember I am dividing this, is that okay? So it is j omega c by, okay. If I define Gm by c, I define omega 0 as Gm1 by c, okay. So this function can be written as 1 upon 1 plus j omega by omega 0, which is like a dominant pole sitting at omega equal to omega 0, because at omega equal to omega 0 the gain is 1 upon root 2, okay, magnitude. So obviously, so it looks very trivial, and it is. I just thought that people think I just copy somewhere and one can always do any time, so there is nothing, great things happen. So a transfer function shows me that if I do this, I can always get a low pass filter this. If I want this omega 0 to be larger, what should I do? C of course will be normally decided by availability of C's. So I must boost GMs. So what do I boost? Bias current. K of course is, if it is fixed once I cannot change, maybe 4 at best you may put. That means I should change the bias current. So the low pass filter with variable cutoff is now possible from V control, okay. So I change the V control bias and I have different cutoff for the low pass. So it's a tunable GMC filter, is that correct? It's tunable GMC filter. That is the fun of OTA, that OTA allows you to do such tunability. Otherwise what will happen, for every case you will have to RLC, you have to adjust, and you can't change inside a chip. You have only a pin which is V control outside. So you have to only play with that, and still you are able to actually design a filter of your cutoff values. Is that clear? Stability is somewhere better because there is a single pole and there is no question, and it is always on the left half plane. So system is inherently stable. Okay.
So even a varactor will give a tunable filter.
Yes, but varactor is some kind of a pseudo active device, because j omega c is not direct, under root of b it comes, 1 upon under root of b. Now whenever there is some kind of such relationship, the CV is parabolic. That means certain range you cannot separate the seeds. Okay. You understood what I said? If the curves are sharper like this, somewhere at very small values, the C values are can't be figured out how much. Okay. Vectors are normally used when you are actually looking for a lot of difference, that is in VCO will use it actually, max min values. So I will use one value here on the curve and one value other side. Then I have range of this I can use, which is what VCO wants, okay, voltage control. So in voltage control oscillators, we will use diodes or varactors, okay, is that okay? But as I say here, that voltage which you, as I say, is which range is very difficult to control. So this is much easier to control, just, okay. Is that okay to you? So this is what I say, that this is a low pass filter which I can create out of a simple OTA by putting, if I want to put a high pass, what should I do? Where should I put a capacitor? In the input side, okay, and still keep it negative feedback. Please remember, system will become unstable as soon as I remove the negative feedback, okay. Of course, this is not the course I should talk. Please remember that whenever op-amps are used, we always use this equation in all our circuit, that V plus is equal to V minus. This is very suspect function, okay. Some other day we will use it, that this is not true every time. You must verify this statement, okay, and that is why the worry starts, okay. So is that okay? Low pass filter. So I also did, for the sake of it, of course this I got it, did home, so that speed. I just showed the technique. So this is the technique which I used. I want a high pass filter, so beyond the frequency of omega 0, I want everything to pass. Below that I don't want anything to pass. Okay, this is not omega 0, maybe this is. Okay, so I used same OTA. Now I put V plus as ground. I put capacitor in series to my input and took a feedback from V minus V out. And then same equations I can use. I out is a function of V in, V minus times this much. I out into this GM VR. I just write down these expressions. Just write Kirchhoff laws. Okay. One equation is coming from V in minus V5 upon 1 into J omega C is the input current, which is same as the IF current, which is opposite of actually I out currents. So you calculate this and adjust the two currents and figure it out what is V0 by V in. You note down if you feel you cannot, but otherwise the function I got therefore is J omega by omega 0 upon 1 plus J omega by omega 0, which is the trademark for a high pass filter with cutoff at omega 0. Is that okay? So now I got two circuits. This is a high pass filter with a capacitance here. A low pass filter, where was the capacitance? At the output. Oh, so now I got trick. I say, okay, I have a low pass and I have a high pass, and if I properly make the two combinations, I can make a band pass or band reject, because depending on the cutoff of which I can, let's say if low pass filter cutoff is higher than cutoff of a high pass, it will become a band pass, but if it is the other way, it may reject that band between the low pass and the high pass. So it is only a matter of adjusting cutoff for low pass and cutoff for high pass. So what essentially the chip available to you is a backward filter with OTA, which is general purpose. In the sense, all four filters can be obtained by using the same block, by just putting three input terminals, different voltages, either zeros or 1 or V or 0, and you can now create out of those blocks any filter, a low pass, a high pass, a band reject or a band pass. Another filter which is required very often in the case of communication in specific is a notch filter. So you can now think how to the notch, you bring omega zeros very close, okay, and you can create relatively good notch filters. Okay. So there are the same backward can actually be implemented for low pass, high pass, notch, band reject, band pass, and that's the fun of this backward filter designs or backward filter chip available. This is available chip, so it's nothing great. Notch, it's not really band pass, you can say band pass with 0 here, okay. But since the 3 dB point anyway slopes you down, you can adjust the two slopes such that the omega 0 is common. Is that clear? It's a band pass at one frequency, okay. It's a band pass at one frequency, okay. But there is a noise associated ahead because of the slope down. So some part of the frequencies are passing, but mean is input directly at that frequency is maximally output. Okay. Okay, so you understood this is omega 0, so low pass, high pass, ek jagah pe it falls down either one. This is the low pass requirement, this is the high pass requirement. So you can understand what I am saying. This is like this. This is high pass, this is low pass. Fix it, you get a notch. Okay. Of course, this is not very easy because to get exactly this value for the two GMs which cannot be easily adjusted. So it depends how much notch you have. This notch has very high Qs. Many circuits require very high Q circuits. So these are required for high Q circuits. Okay, so think of it. So I am just trying to tell you where simple things which we have can be implemented and realize whatever you are really trying to achieve in your actual hardware. Okay, okay, so here is the circuit which is the quad one, backward. There are two OTAs available. Right now I assume them that their GMs are same. On a silicon chip this is not a very wrong assumption. As close I can make, their properties can be almost identical. However, on chip there are many chips, so one can 100% guarantee, but one believes at least at that area the two GMs will be equal. This GM may not be same as the other chip GM exactly, but on chip they will be same property can be held actually. So this capacitor is here, this line has come, so please don't draw that line also because I didn't want to redraw again, so I just interposed capacitance there. Okay. And this is a typical circuit which can implement everything, that is low pass, high pass, band reject, and even notch if omega zeros are adjusted. Of course, if I only want LP, I can do one GM itself, only one HP, only one GM circuit. But if I had to make three such separate chips, that's much costlier. Okay. So I will give you one chip which makes all of it. Okay. So I repeat, I can certainly have a chip only for low pass, only for high pass, but then I will have 3 chips to do or 4 chips to do each function, so which I will not like. So please I repeat again, this is a C1 in series from this node to the V2, and there is nothing in between, there is no shorting in the capacitor. फिर कल वो मॉडल पे दिखेगा, if a capacitor is shorted like this, what is the output impedance? इसलिए पता दिया मैंने. No, nothing wrong. I think you are justified in writing that. I just feel since it goes out faster, so I thought we shouldn't allow people to see something we are as if intentionally we don't know things and putting things to them. Okay. Now in this case, we start with the case. Let's say the first one was low pass. So okay, let's say whether this creates a low pass filter. So I said okay, V2 and V3 voltages are grounded. Okay. V2 and V3 voltages are grounded. Okay. So only V1 is present, V2 and V3 are grounded. And now we start looking at the identities here. The Vout1 is essentially V plus 2, isn't it? For the second transistor input, V plus 2 as I call is same. V minus 1 is same as V minus 2 and is same as Vout2. Connection, there is nothing very great I am talking about. And V1 of course I say is my input voltage. So start writing now for each voltage. Okay, this small gm sometimes I replaced it by capital GM, so just think right now K is 1. So in hurry sometimes I write small gm. So take it, K is 1, so capital GM is small gm, okay, in case something happens ahead. Okay. So Vout1, I want to find the output of this, it is nothing but the transconductance on this, my V plus minus V minus, so V1 minus V minus into j omega c is the output. This is the current, this is the impedance at this node. Now please take it, this capacitance should be larger than any other capacitance at the input end, otherwise that will get modified. But still they are in parallel, so C may still be little different than the norm, but it's okay. C2, okay, which is Vout1 minus Vout2. Please remember V plus 2 is Vout1. So Vout1 minus Vout2, V minus 2 is Vout2. So Vout1 minus Vout2 into relations Vout1 and Vout2, and I'll just pick up this Vout1 from here and substitute that in 2. So that why I am interested, I am only interested in Vout2 by Vin. That's my interest. So I just will replace Vout1 from this equation 1 and substitute into 2. Okay, so substituting Vout1 in Vout2, so I get Vout2 is Gm by j omega C2. I substitute Vout1 from the earlier equation and corrected terms. So I got ये Vout2 इसकी टर्म है, एक Vout2 इधर भी है. This whole I have shifted on the other side. So Jm omega C2 by Gm. Okay, that's what has happened. I say I started using small ones. Okay. Into Vout2 is Gm 1 V in upon j omega C1 minus of Vout2, which is minus Gm1 j upon C plus into Vout2. Collect the terms. एक ये टर्म है और एक ये टर्म है और फिर सबको उधर ले गया. All Vout2 terms were collected by me, which gives me 1 plus Gm by j omega C1 plus j omega C2 by Gm1 is equal to Gm1 by j omega C1 into V in. So the transfer function of the gain aj omega is Vout2 by V in, which gives me this function Gm by j omega C1 upon 1 plus j omega 1 j omega C1 plus j omega C2. If I replace for your standard thinking that j omega is nothing but the S, which is what if I go into the S domain or if I am in the frequency domain, then kind of function I am going to get. So if I replace it by AS, this is Gm by SC1, Gm by SC1, SC2 by Gm1. Collect the terms now. So I get Gm1 square upon S square C1 C2 plus SG1 C1 plus Gm1 square. If I put some constant looking things, then this is C upon AS square plus BS plus C. C is constant, Gm is a constant value. So two poles, one of them is dominant, which is the cutoff frequency for this low pass filter. So which are the voltages I made 0? V2 and V3 I made it 0. And V1 I put it as Vn, and I got from the same a transfer function which represents a low pass filter. Is that okay? Let's do the next one. So this is so what is obviously are 3 voltages. You make in other case other 2 zeros and one of them, and in the 1/4 case what can you do? 2 of them you make availability and one of them you make 0, so it will be the next 4th one. Okay, so we'll do one, will not do all of it, I'll just show you the two of them and then you can repeat the other ones. So is it okay? So if I use the same circuit now, V2 is Vin, okay, but V1, V3 are 0. Is that okay? And I believe it should give me high pass, I believe it. So let us see. Okay. By same method which I followed just there, I figured out V out 1, I figured out V out 2, substituted V out 1 into the equation for V out 2 which I did just now. Only thing now that a slight change has occurred, this voltage plus Vn is essentially the output. Is that clear to you? Whatever is I out times this plus, because that is at above, that will be additional term which is appearing there. If this would have been grounded, this term would have been 0. Okay. This is series, two battery in series. Okay. So I collected V out term is minus Gm1 V out 2 by J omega C1 plus Vn, and V out 2 is same as Gm1 V out 1 minus V out 2 upon J omega C2 is 2. Substitute this V out 1 here and solve for V out 2 by Vn. Is that clear? I repeat, substitute V out 1 here and then collect the term for V out 2, and other side we leave the term for Vn. V out 2 by Vn is the transfer function. You know, many times book do not solve, so मुझे भी कभी कोई doubt होता है कि are they okay or not. So I solve and check whether things are okay, and luckily they are always right. Once I wrote to Rosalie some mistakes which in the newer versions they have corrected. Okay. You know, every step does help to know how it is done, but it doesn't give any physics ahead of it. Okay, it only tells you how to substitute. So arithmetic ही इसमें हो रहा है या algebra कह लीजिए, I don't know how it says, but that's that, all that. So if I substitute 1 in 2 and collect terms for V out and V in the other side, and I get these terms again, and I get the transfer function as 1 upon 1 plus SC2 by GM1 plus GM1 by SC1. Okay. And if you see, if I take this SC1 and multiply numerator by GM1 SC1, so that goes up, this becomes GM1 SC1, this becomes SC1 SC2 into S, that is S square C1 C2, and this becomes GM1 square. Okay. Just multiply numerator denominator G1 into SC1, दोनों तरफ multiply करो, ऊपर और नीचे. So you get a term which is G1 SC1 upon S square C1 C2 plus SG1 C1 plus GM1 square. If this is G1 MSC, GM C1 is called constant D. So D into S upon AS square plus BS plus here D को divide कर दो तो A0 some new other constant, S upon A0 S square plus B0 S plus C0 is the transfer function. And you know, whenever the transfer function is S upon S square kinds, this is A representing a high pass filter. Okay. And its dominant pole will be the cutoff point. Okay. Oh sorry, this is S, it is a band pass. Okay. If what would have been high pass? S square, yeah, sorry, it is band pass. Okay. So let's see, the two frequencies are omega 1, omega 2 is essentially the band in which outputs are 1, transduction has the magnitude of 1. Okay. So this is a band pass filter, as I say you are right. By same argument, if I make V2 equal to Vin and then make V1 equal to V3 equal to 0, the 2 OTA, I mean this is what we did right now, 2 OTA architecture behaves like a band pass filter. We can do something interesting now. If V3 is Vin and V1 V2 is 0, by same method which I did, I can get a function of S square C1 C2 upon S square C1 C2 S C1 GM1 square, which is the transfer function for a high pass filter. The only filter we have not yet done is band reject. So बैंड रिजेक्ट में क्या टर्म आती है मालूम है क्या, यहाँ पर एक और प्लस टर्म आएगी कांस्टेंट की, तो वो बैंड पास और बैंड का उल्टा हो जाएगा. Okay, so let's. So if you have seen it, denominator for all of them is same, S square C1 C2 plus SC1 GM plus GM square. This is denominator for all four of them. The filter is only on the top, I mean whether which kind. Okay. So if I put the final filter, which is V1 is equal to V3 equal to Vn and V2 equal to 0, then I get this transfer function S square C1 C2 plus GM1 square upon the same denominator, and this represents a band reject filter. I repeated, I think someone was or should not be worried about. This essentially is being told all that I am saying, sorry, omega 0 1, omega 0 2, I adjust two blocks and the in between there is nothing, and therefore it is rejecting those frequencies in between. Okay.
Omega naught 1 and omega naught 2 will not be simply that GM.
Not, but equivalently saying it is. The problem is that one loads the other, which in this case we have taken care. If we are only independent, then we don't feel the loading of the other. The reason why I showed you this was that it takes care of the, when you connect, it loads the next stage. So we know what is happening because of the second stage. If you are independently this, and when you want to connect, in independent design will not take care of load unless you know what load I have to use there. If that happens, it is same as what I did. Is that okay? You are, I mean, what you are saying is I can use two blocks, but then I may not get this. Just by when you connect, the connection makes the difference, and that's the circuit I have shown which connects the two blocks. Is that okay? So this fact has to be understood that if I have a two-stage amplifier, I may design a first stage. I must jolly well know what is the input stage or input of the next stage, because that will load my first stage. So if you don't take care of that, then your design will never be correct, because the actual loading will deteriorate every performance. Either first evaluate. Also you must know this also loads the one and this also loads the other. So both sides, the output and input impedance have to be matched, and then only power is maximally transferred. So game is to be played when you connect the things. Okay. And I said to you that okay, this OTA can also be used as an amplifier. So let's say if I have a normal amplifier, is that okay? This you have done. So this is something, a chip which is available from TI, it is available from analog device is available, national chip is available. Of course now national is again TI, but chips are still national numbered, so these chips are available. But I must tell you that there is no chip which takes you whole of a band. What they will do, there will be still 8 to 10 chips, which will be, because otherwise the GM value will be too bad for them. So they actually adjust band-wise filters. Okay, that means from this megahertz or this kilohertz to this much, then this megahertz to this. So each has a band of this in which this operate. Though theoretically 0 to anything is possible from this. Okay. So that is why they can make lot much money. You want this, you buy this. Okay. Okay, so here is something, last part of my theory. Okay. We have been doing this standard op-amp based amplifier, so I actually connect the same OTA in a op-amp feedback kind of thing, Instead of you asking me how I solved, you either note down, I will not say more than that. I have solved this as I could. Okay. The reason why I put it, because this is V minus it is used, so I change the sign there, but otherwise it's okay. So I figure it out, I0 is minus Gm times this much, Vn minus this by R1 is this current, but this current is, so in this criteria, the criteria which all of you should know, and that is the one which again I repeat and verify yourself. In all this analysis we say no current enters the terminal input of the terminal of a OT or op-amp. The reason is to be, that means the input impedance should be extremely high, okay, and the negative feedback dominates. This is the second condition which allows you to do this, okay. So if that is not, so real circuit you solve and figure it out, if both conditions are met, only then these statements are valid statements. Okay, so then this minus this is something, I0 is minus I2, collect the terms, find I1 and I2. Yes. The reason is in op-amp, if you see it, the currents are always shown in this direction. That essentially it is minus of the actual current, but in op-amp if you see, currents are always shown in. If you see a op-amp equal, this is for the thing which is equivalent of an op-amp. If you see any op-amp circuit, we show I current in. Okay. No, this is different case. I am only saying the difference of this into Gm is the output current. Yeah, it is Gm times V plus minus V minus. No. This current which is coming here has no other terminal to go, so the current here in this arm is same. This is only a matter of node. At that node the current is same. No. But please remember, the impedance seen from here to here and here to here is not same. When I say this, okay, well, at best you can say here. Okay. But there is no other node, so this currents will be equal actually. Opposite sign, that's why I added. To add it, I said they are opposite sign.
You should point outside.
That's what I say, that in all op-amps we put inside this, so I just equated it. Okay, so think of it here, thoda second there फिर से करो. Okay. Yes. No, because this current essentially is moving this, and I assume the direction opposite, I put it minus. This is only a question of putting minus sign for the equivalence you are doing. Okay. सॉल्व करके देखो यार, मैं कर रहा हूँ तो तुम भी कर सकते हो. Okay, so I calculate I1, I2 and then equated I1, I2. At least that you agree, I1 is equal to I2 because there is no current enters the OTA. And I substitute all this expression here, and I get a very interesting relation, V in by R1 minus V out by R1 upon 1 minus Gm R2 is equal to Gm by 1 minus Gm R2 into V out. Collect the term for V out and collect the term for V in and get a ratio of V out by V in. ये नोट डाउन कर लो जो मैंने लिखा है. Because in negative feedback system, the output will be V0 is out of phase of that, and therefore if it doesn't come minus R2 by R1, you will start telling me where is minus sign came. Now I want to bring this, and that's why I assume the same direction as op-amp uses. Okay. So yesterday I was telling that under certain conditions only OTS behave like a good voltage control voltage sources. Okay, so the condition will now bring it soon. What could be the condition? Anyone quickly? GMR should be very, very high compared to 1, which many times you can always attain in OTA. That's the purpose of OTA, GM is higher. Okay. So if you don't use very small r's, then GMR will be very large compared to 1, and then equations will be same as an op-amp requirements. Okay. Is that okay, everyone? Expressions? Okay, so I figured out the gain V out by V is 1 minus Gm R2 upon 1 plus Gm R1, and yes, if Gm R2 and Gm R1 are much larger than 1, V out by Vn is minus R2 by R1, which is what an op amp would have given. Say OTA with these conditions behaves like an op amp. Is that correct? So it is not my condition, this was not necessary to show, only I was saying that many times people believe if only OTAs are on chip, how do they make op amps then? Things are possible even using OTAs. Okay. I agree that to some extent the load has not been shown to you. So if I put a load, that will take care of this actual impedance going down. Your viewpoint is very correct. If I open ended, if I see yes, there is an issue. But as soon as I load it, that will be the output resistance. So in that case, it will behave like an op amp output. Okay, you have a very good point. All I was saying that in real life, people use this and say, and they don't think, but they get the correct answer. So why is the reason I said this is how they get it actually. The last part of op amp based this is now one of the last part which I thought today, of course I will not do all of it, I will only show you the basic, but something which is very relevant for those who have per se interest in joining a company which has more interest in mixed signal design, like Broadcom, Qualcomm, okay, who are more interested in analog plus digital on chip and RF as well. These chips require fully differential amplifiers. Okay, they require in many applications fully differential. Now this fully word was essentially inputs are always differential. So what is a fully means even outputs are differential. Therefore it is called fully differential. Okay. Some books, some journals they only say difference amplifier. But then I don't know whether difference at the input or some write difference output amplifiers, which is also equally good way of telling. I have followed some books which says fully differential. I use this terminology, nothing very different, all that I am saying two input, two outputs. Okay. Is that this is okay? So we start the last part of op amps. As I said, there are too many things in real life actual designers should learn to do themselves. But where to do and how to do is our course is trying to help. I cannot replace everything. I can only tell you why I look this way. For example, now I will show you how to get some things which is worrying me in this, and that is the idea that if there are variations, what do I do? Okay. So I will show you this later. So this is a fully differential op amp which essentially says if I have V minus V plus out inputs, V out plus, V out minus, and they of course are opposite terminals, phase change. So this is V out plus, this is V out minus. Such systems are called fully differential amplifiers or differential output op amps. So I keep telling they are mostly used in mixed signal designs. For example, if you want to make an analog multiplier, which is essentially a digital requirement, so you can use such circuits to actually quad multiplications as they call quad multiplier. We can use analog blocks to do digital functions. So real or in ADCs, some of the ADCs you require differential outputs. Okay. So these are essentially for mixed signal blocks. Okay. There are advantages and there are certain, whenever things happen good, obviously there must not, everything must not be good. Okay. One other thing which is better for two-ended outputs or double-ended output compared to single-ended is, since the output there is limited by the, like in a cascode or a buffer, you VDD minus that much, okay. Because each is controlled by the same I5 currents, okay. So there is a difficulty there to manage swings. This may have much easier way of because you can independently handle this and swing may be much higher. It may also have a better frequency response or bandwidths simply because there is no Miller poles here. In the normal stage you put CC, you did stability but you lost the frequency bandwidth. There is no Miller pole here and therefore or Miller feedbacks, therefore it will have a larger bandwidth requirement. So in sum this, maybe before we quit, last slide also on this same thing. The biggest advantage of fully differential system is the rejection of noise. Of course, along with the noise something else we'll talk, a few minutes we'll talk. Let's say this is my fully differential amplifier and there are two parasitics at the two inputs and there are two parasitics at the outputs, capacitances. If I now see some noise signal comes at the input, is that okay? And our belief cannot be very absurd if you say the noise at the two terminals there will be two different noises. It's an unlikely event. I am not saying it cannot happen, but unlikely event. So what will be the actual V minus it will receive? This plus noise which is charging this capacitor. If these parasitics are same because of the symmetry you have, then this noise sitting with this and this at this terminal noise sitting with the other, since both gates noise added to their input, the difference will be independent of noise. By same argument, if there is a noise coming at the output, the difference between VO plus or Vout plus 1 Vout minus will cancel the noise. So that is the biggest advantage of having a fully differential system. It rejects all noises whether at the input or at the output. We haven't actually, I should have said, but I think some word finally I may say. There is another problem in defense or op-amps. The word we never talked, we talked about CMRRs but we did not talk about PSRRs. So this power supply rejection ratio is essentially because power supply is not constant all the time, the output varies and we believe that that should not vary. It should be, even as so much power supply goes, output should not vary with the change in power supply voltage. This is equivalent of that. So if there is a change, the difference will cancel it. Okay, so PSRR is very high, 100 dB plus in the case of differential systems. Getting 65 to 80 dBs PSRR in the case of normal op-amps is tough. But in the case of these differential systems, they cancel. So any variation is taken care. So indirectly not saying there, but it also improves your PSRRs because it does not allow you any variations at the difference actually. Only assumption is the variation in VDD is same as variation in VSS. If that doesn't occur, there will be some PSRR value which may not be very large but still better than normal system. So is that point clear to you, that why differential systems are preferred in certain stages, and so what is the difficulty with them? Because the difficulty is now going to be shown to you a few minutes and then next time we will solve that difficulty. Okay. Is that okay? So the fully differential systems reject noise as much as possible, and it also does one more thing. Can you think another noise kind of thing is something related to what we call offsets. Offset is also, what is an offset of an op-amp? That if the inputs are made 0, output should go 0, and if it doesn't, we actually some way adjust V minus or V plus so that for that the output goes 0. Here it cancels because any change in both difference is also cancelled out. So in every sense, differential amplifier seems to be very good. But if we see you want this, do you think it is actually two op-amps I am using to create a differential amplifier? एक ऐसा. So I am essentially using, equivalently saying, two op-amps together, equivalently saying, okay, and one trying to cancel the bad part of the other. That's the one part in this. Okay, is that okay? So we'll see what is the major worry soon, and next time that is the circuit I'll solve for you. There is an issue which we will say the common mode voltage as it called. For CMRR to be high, we want the two devices should be as identical as possible. on diffam, GM1, GM2, everything, W bar, everything should be, and we figured out then that the CMRR will be infinite, everything is fine, delta GM is 0 in the denominator. But that doesn't occur, GM1 minus GM2 occurs, and how close they are, that decides your CMRRs. Now in this case, that common mode voltage is not a constant quantity at all, we will show you next time, and if that happens, at different days it will show you different CMRRs operations, and we will like to hold that common mode voltage, and that is called common mode feedback circuit. So additional circuit is required for fully differential systems, which is called CMFB circuit, which is very important in any real design. The first thing we ask people to design is CMFB circuit, okay, because that will then hold this common mode to a value, okay. We will see that little later. Just to go back to the open circuit and closed loop gains of a normal differential system, if I see the open loop gain of a fully differential circuit, it is nothing but V out plus minus V out minus upon V plus minus V minus, okay. If you make a single ended, make one of the output 0 or don't consider it. So V out plus upon, so it's nothing that I cannot make a single ended, one output divided by difference, I still have a single ended output. So it is not this that this cannot be used as a single ended, it can always be used as single ended. But then the major advantage of noise, everything is lost. Then why do you use double? You can as well as single ended, which is much more stable, everything is so good actually. So if we consider one of the output is fully differential case and use negative feedback similar to that of a single ended op-amp as shown here, here we invoke the rule that Rin is very very large, or to say currents do not enter op-amps or negative or positive inputs, then only we say V minus is V plus. This is we are invoking proof we have done earlier some way. So a closed loop gain then would be minus R2 by R1, open loop of course V0 by Vn, whatever it is, okay. Extending this to a differential case, then the VO plus is the opposite of U minus. If I extend this to this, it will be opposite of that, okay. Once I say this is like this, now as if I am now telling that it has a 2 diffam there, a 2 op-amp there, okay. You note down this, and I will show you the equivalent of that. Please don't think I actually put 2 different op-amps there, I am trying to say equivalent of this is what is inside. Okay. So fully differential amplifier can be realized from 2 single-ended differential systems, okay, differential amplifiers. J input, ek output, J input, ek output. So as if 2 systems are going on. Okay. Is that clear to you? 2 inputs, same inputs, 1 output, same input, other output. So as if those system has. This is the last slide for the day, and we will start next time with CMFB circuit and why it is needed more. Okay, last slide for the day, not last. This is equivalently saying there is a differential amplifier can be, fully differential amplifier can be created by using 2 single-ended normal amplifiers, diffams. Okay. So the way it is, you have one diffam whose inputs are V minus and V plus, the output is, and the other one input is grounded, the other is taken as a part of this resistive network. We will talk about this later next time, and we will say now these two systems together actually gives you VO plus, V out, which are equal but in opposite phase. This is given in Boyce and Beckett's book. So what is the problem with this system, which is I wrote down, which is why we'll have to do something more about it. Please don't think that this is how I am implementing. I am just trying to say the principle of fully differential system is essentially equivalent of this. You can see from here the difference voltage is divided equally, and that is being fed here, which makes this opposite. Okay. R upon R plus 2, 2R, the ratio is adjusted so that this actually gets equal and opposite in signs. So this is the game which we are playing there, but just wait next time. The catchword here is essentially because the two defines do not have identical inputs. So if you use all your stability criteria system there, the phase margin associated with the two systems are not identical, and if you connect them, the worst will come. Okay, and therefore essentially what will happen that the bandwidth will get hurt maximum on this. So we started with saying that fully differential system has higher bandwidth, but if you realize it like this, then you may find your bandwidth you are losing actually. That means something I must hold greatly correct so that my bandwidth is not affected. This is the catch. What is that? Common mode feedback CMFB does every time. Okay. Essentially what is common mode voltage? V out plus V out minus or this divided by 2 average value of that. I want to hold it, but if V out changes, then how do I hold it? That means subtracting out of max must be same as adding to the other so that the average value remains constant. That is what common mode feedback does. It holds that value. Okay, and if it holds, then much of your problems are solved. So next time, is that point clear? So this will be first 30-40 minutes. I will finish this EMFB, which is, as I say, is very important. All those in real system will use everywhere CMFB circuit will be there, and we'll start with the noise next time.